previous video, we've seen what tensors are, and why they are so interesting to describe our physical world. Now, in this specific video, we're going to look at a particular type of tensors called the metric tensor. And we're going to see that it's key to understand how our physical world works. The metric tensor. By the way, metric here has no direct link with metric system, It comes from Greek, metrikos, which means which can be measured. And originally it was concerning verse line lengths in poetry, So it's yet another link between poetry and mathematics. Anyway, so the metric tensor is, as we said before, a very important math object because it allows to measure elements using the geometry of a vector space, and it therefore defines how to measure distances in the concerned space. Now, one example is in 3D Euclidean space. And in this particular case, which is also called Riemannian space, the metric tensor simply is the Euclidean dot product, that allows to define distances, etc., in 3D space. The metric tensor is a bilinear form, since it's a tensor, of course, and so it goes from v cross v, the space vector, to the field, that the space vector is built upon. So it's a 0-2 tensor. If you don't know what that means, well, you have to watch my previous video on tensors. It can be defined like this, just a formal definition. Now, once a basis has been defined, then you can, of course, represent it using coordinates, and in that case, covariant coordinates. And again, if you don't know what covariant means, well, go watch my video on covariance. Anyway, so this is what it looks like, S being a scalar here, which is a member of K. In other words, a number. It could be a real number, a complex number, or something even more complicated than that, provided that it's part of a field. And this, in Einstein's notation, is written like this. In other words, you skip the summation here symbol, and makes things look simpler. Now, in matrix representation, once you have this basis defined, it becomes, like this. So the Gij is equal to this, the vector here is here, and the vector there is there. And so you can develop it like this, and eventually you get something like that. And that, again, using Einstein's notation, is exactly what we were looking for. So that's good. Now, the metric tensor can also be applied to a single vector, something like this. And it becomes then a linear map from the space vector to its dual space. Now, this process, as you can see here, is called index lowering because, well, as you can see, the index goes from the upstairs here to the downstairs there. And that allows to convert contravariant coordinates of a vector to its covector covariant coordinates, and this is a proof that we can do that here. I'll let you, go through it. It's pretty straightforward. And so the metric tensor allows to transform the contravariant coordinates of a vector to the covariant coordinates, and this mechanism can be generalized to any contravariant tensor index. So in fact, the covector, the covariant vector in dual space of a vector is the image of that vector by the metric tensor. So it's kind of a measurement of the vector, using a specific rule, which can depend on the type of space we're in, if it's a flat space, a curved space, a quantum space, or whatever. And finally, note that if you use a contravariant version of the metric tensor, in other words, a version with the upstairs indices, well, you'll raise the index of a covector to obtain its dual vector, okay? Now, let's see some examples, in simple spaces like, the classical Euclidean 3D space. Well, in that case, a metric tensor is pretty trivial, Using a canonical basis, it can be written like this. And applied to 3D vectors in that space, we get something like that. It gives you again the definition of the dot product. So the metric tensor defines the Euclidean dot product, and its component basically are equal to the Kronecker symbol here. Now, the distance between two vectors can be defined as the norm, defined thanks to the dot product of their difference, like this, okay? And then you get the well-known dx2 plus dy2 plus dz2, okay? Now, a space for which there exists a frame of reference where the S square is equal to this is called a flat space, and we'll use that definition. So another way to say it is that a flat space is a space where you can find a frame of reference with Euclidean coordinates, which means where the set of coordinates allows you to define a distance such as this one, here. And that means that there is a frame of reference where Gij is equal to delta ij for all points in the space, okay? So note that all of this, also means that the definition of the metric space in the end allows to determine how different two elements of the vector space are. Now, another simple case here is in special relativity, and in which case the 3D space, the Euclidean 3D space becomes a 4D space. It's called a Minkowski space. And again, using canonical basis, the metric tensor becomes this, and the only difference is, you have one more coordinate, of course, because it's 4D space-time. And the first one, is like this. So beware of the minus sign here. So applied to a 4D vector in space-time, we get something like this, again, once you have defined the canonical basis here. Which is equal to this, which yields to a distance defined like this. And again, because it's a tensor, that means that when you define the distance like this, the rules are the same for all frames of reference, and that's why special relativity works, basically. And also note that if you use a frame of reference where you say x1 here is equal to ICT and x2 is equal to x, x3 to y, and x4 to z, well, then that you can see that the Minkowski space is actually flat. Now, here you have a square here, so it should be positive, right? Now, in order for ds squared to stay positive, dx squared plus dy squared plus dz squared has to be greater than the C2 dt2 here, or here if you prefer, which correspond to space-time events with a velocity smaller than the speed of light. And we call these events time-like events. For other events, which we call space-like events, we need to use another definitions, and it will be c squared dt squared minus dx squared minus dy squared minus dz squared. And finally, space-time events where ds squared is equal to 0 are called light-like events. But we won't have to use that here. I'm just saying that for your information. And because I'm a very nice person, of course. Now, finally, here, in general relativity, you can see in Einstein's field equations here that the G mu nu tensor, the metric tensor, is applied to scalars, r and lambda in that case, to reflect the geometric curvature of space-time, which is due to surrounding masses and energies here. But we'll see that in more details in the next video. See you there.